In this video, I'm going to give a quick informal overview of what is meant when we talk about the derivative in calculus. And so this is kind of like a pre-calculus approach, not a like formal calculus approach yet. It's just kind of a discussion of what the derivative is. And so we're going to start by kind of defining by saying this: the derivative is kind of a general rule. Okay, so we start with a rule that basically tells us the slope of a graph at any point. So it is a rule for slope. So let's just say this: for most functions that we are given, I could give you another function. We'll call this like f prime of x, mostly in calculus, but we say the derivative, and what happens is when you plug an x value into it, it'll tell you the slope of this graph. And so let's start with this really quick conversation about slope here. But basically what I want to bring up is this: let's assume, say we were in like a bicycle race, and so like the race starts, and we could measure how far you've gone over time. And so we could say distance over time. And just keep in mind, like we could discuss this as like y and x. X is input, or y is output. Sorry, distance in time. So distance in time. I actually got these backwards. So we say time and distance. Okay, but we say this would be like x and this would be like our y. But we say after 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. The bottom line here is this: if you could go like a constant 10 miles per hour, measuring your distance in miles, we say after 1 hour you'd be 10 miles. After 2 hours you'd be 20, 30, 40. 50. So, by examining this table, the first thing I want to point out is what we mean by slope is kind of like how fast, our function value is changing. And in this instance, we're saying it's changing like plus 10 miles for every 1 hour. And so this is kind of a direct relationship here. As a matter of fact, this would be like the function y equals 10x kind of thing going on. Or we could say distance is equal to 10 miles for every hour, okay? So when exploring the graph of this, we talk about rate of change. One thing I want to bring up is this. This would be a graph where we had a y-intercept of 0 and say a slope of 10. So I'm just going to kind of say that this is sort of a slope of 10 here. But this would represent time and distance as a function of time. So when we look at this graph and we say, okay, so what is the quality of this graph that tells us how fast something was changing? What we're doing is we're exploring this idea of slope. And so up here, previously we said, going up 10 miles every hour. Could we have said it goes up every, 2 hours, it goes up 20 miles every 2 hours. And the fact of the matter is, we could do this, we still end up with this 20 over 2, which is this rate of 10 for every 1. But when we talk about rate, we're saying 10 miles every 1 hour. So what we're really doing is exploring slope when we talk about a speed. So we call it slope. How does one find the slope of a graph? Well, easily done. As a matter of fact, we just measure what we say is rise over run between 2 points on the graph. So we'd say, okay, so this is like my change in y. We'll call this delta y. Get into that more later. This is delta x. But if I were to say slope of this line would be delta y over delta x, what I want you to realize is in a constant case like this, if you could ride your bike perfectly 10 miles per hour, that'd be great. Your slope of your graph would be a perfect line. Now, real life, of course, is not exactly like this. It might be more like something like this: time and distance. We say 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and say we go like 12 miles per hour for like the first 2 hours. So up 12, up 12. We go up from 0. I should include 0 here. 0, 0. So it went up 12, and it goes up another 12. So our average rate of change is like 12 miles per hour. And then when I go up maybe like 10 the next hour, so I only go up by like 10. What's happening? Well, I'm getting tired. If I went up 6 the next hour, I had to go up a hill or something like that. Plus 6. Oops, I was thinking 6, so I wrote a 6. If I went up 6, of course, we'd be at 40 total miles, and we would have gone up 6. And let's say I go up 2. I'm just absolutely pooped. The fact of the matter is, if we were to graph something like this, what you'd see is more, and this is more of a general graph. You'll have to forgive me. I'm just kind of doing this to get the idea across. But we say we started at a distance of 0. We went up really fast at first at a constant rate. We're looking at the slope of this line, but then we kind of slowed down to 10 miles per hour, then 6 miles per hour, then 2 miles per hour. The reason why I wanted to graph this is because the derivative, again, really wants to ask this question: what is the speed at any given point on a graph? Like, so for example, what was my speed right here, and what was my speed right here? And what you realize, or you start to realize, is this: in an ideal situation, like over here on the left, speed is always constant, but in real life, speed is not a constant. As a matter of fact, you'll notice even on this graph, we had to connect the dots in between with straight lines. The honest to goodness truth is, most of the time, let's consider that my distance over time might even look something like this. Distance over time. I started off really fast, and then here, and I slowed down a little bit, and then, oh, maybe I forgot my wallet, I had to go back, and then I reached the finish line, and I reached my total distance. Here's the distance to the finish line. Good for us. And really what I want to ask is this: how fast was the bicyclist going, say, at an individual point in time? An individual point in time. So now consider this in the past two examples. We said to find the slope of this line, I need 2 points on the line here. If I wanted to say find the slope of the line right here, I could do this. I had 2 points. We'd say reference this point up here and reference this point up here. We could say I went 6 miles in an hour, so that's 6 miles per hour. But on a graph like this over here, you say how would one necessarily find the speed at this exact point? And so if we're going to discuss the slope of my graph at this point, we need to accept this principle, and that principle is this. The slope of the graph at this point would be the same as the slope as a line, okay, that is tangent to my graph at that point. So this tangent line right here, we could find the slope of it using some rise over run, just like this. It's just that it has the same slope as my graph right here. So if you want to know what the derivative is, the derivative basically tells you the slope of the tangent line. That's all it does. It tells you the slope of the tangent line. So here's what I've done. I actually graphed the graph of, you can see this here, this is the graph of y equals 1/10 x squared. And I didn't do just y equals x squared because I wanted you to see a really wide graph, give you some real estate here. But you'll notice this, we say, here's my blue curve, 1/10 x squared. And what I've done is I dropped a point A on here and passed a tangent line through it. But what if my question was this? Hey, you know, how fast, if this represents my distance over time, like how fast was I going 1 second after, you know, I started? So what I'll do is I'll go back and I'll drop this point over 1 second here. We could kind of zoom in a little bit. Say, drop it over 1 second if you can see this. But we say that what's the slope of my graph at this one point? Well, it'd be the same as the slope of this red line right here that is tangent to the graph at this point. So we could actually approximate the slope of this graph just by saying approximate the slope of this line, which is easily done. I'd say we could probably say, well, from this point here, what if I slid this point back to here? Okay, we say maybe it went up about 1/3, as you can see on my graph here. I'll zoom out a little bit more. Actually no, it went up about a half. Sorry, my scale was off here. Went up a half over 3. We say up about 1/6. Okay, so the slope of this line would be like roughly 1/6. If I wanted to know how fast was my graph changing when x equaled 2, well, then we'll say what's the slope of the line tangent to the graph at x equals 2. And so we could estimate the slope of this line. We say it goes from about a half up to, say up 1 over about 1, 2, 3. So it's about a third now. So you notice our slope increased from a 1/6 to a third. If we were to keep going here, there's not necessarily there is a pattern, that is the derivative, but we say now if I wanted to find the slope of my graph, for example, at 3, we'll just draw a line tangent to the graph at 3. Just notice this. When the graph is neither going uphill nor downhill, I'm saying the graph has neither negative slope nor positive slope, it has a 0 slope. It is not changing. So its rate of change was 0 here. And actually a graph can have a negative rate of change. We say, what is the slope of my graph? Say at -5. When x is -5, what's the slope of my graph? We say, well, the slope of the tangent line would be, it looks like about down to kind of over 2.5 kind of thing. So we could modify that as about -4/5 or something. But the point is, you can always estimate the slope of a graph at any point just by drawing the tangent line to the graph at that point and finding the slope of that line. So in my next video, we're going to discuss, well, how do you find the slope of this line like at every given x value? Not just estimating, but the exact slope of this tangent line, which is kind of a fun thing to do. We're going to derive the derivative. So I hope this video helped people to understand what we mean when we discuss we want to find the derivative of a graph. We want to find the speed of a graph at an instantaneous point.